Hello, welcome back. Today we're going to continue with our lecture series, and the topic of today is the mathematics of Disney and Pixar. Pixar. Now, this is a very simplified version. They do more complicated math than this, but this lecture should get you started, and you understand how vectors and matrices are actually quite useful for them. Okay, so we can visually interpret vectors in two different ways. So if we have a vector like this, we can picture them as if it's a vector that kind of like draws a line from point zero zero to 2, 8, right? Kind of like this. Another way we can picture them as it's just a point at 2, 8. So those are two common ways of how we visualize vectors. Now, when we take a vector and multiply it by a matrix, what we're doing is we're transforming the vector. So, for example, that was the vector we were just looking at, 2, 8. If we multiply this vector by some kind of matrix, well, notice how if we multiply this out, it gives us another vector. So essentially, we started off with this vector and we ended up with this vector. So when we multiply a vector by a matrix, we're kind of transforming the vector into something else. Okay, so you can see that matrix kind of acts like a function that transformed the original vector to something else, and that new vector might be something we want more. Now, if we look at the right figure, one way we interpret it is that we started with this vector and then we transform into this vector. So that's like a vector transformation. However, if we picture vectors as dots, so you started from here, it ended here, right? So you kind of move the dot from one, well, it's more like teleport. You teleported the dot from here to here, okay? And that's what the matrix did. So today, what we want to do is basically study how the impact of matrix on vectors, the various type of impacts. So if we start by looking at the simplest matrix, the simplest matrix is called the identity matrix, which we write most of the time I. And the identity matrix is basically the matrix that does nothing. If you put a vector into the identity matrix, you just get the vector back. So it's equivalent to multiplying x by 1. So the identity matrix is kind of the matrix equivalent of 1, which does nothing. So if we have the identity matrix is dependent on the size of the vector. So the bigger the vector, the bigger the identity matrix. So for example, let's say we have x. So the identity matrix for x looks like this, and the identity matrix for y looks like this. Basically, the identity matrix is the case where you got zeros on diagonal, and then ones on diagonal and zeros in upper and lower triangle. Looks just like the RREF form that we want to achieve. And it kind of makes sense, right? Why this give us the same answer? Because it'll be 2 times 1, which give us 2, and everything is 0. And then now we have 1 times 1, and everything is 0. So from this multiplication, you can quickly see why this type of structure is able to give you the identity matrix, or that it does nothing basically to the original vector. Now, the identity matrix is always a square matrix, and the dimension has to match the original vector. So if it's 3, it's a 3 by 3. If it's a 2, it's a 2 by 2. Okay. Now, the identity matrix is a good starting point. What if you multiply the identity matrix with some number 3, right? So now you have 3, 3. So instead of doing nothing, it's actually now stretching the original vector by 3. So if you look at this here, 1, 1, if we multiply the identity matrix times 3, that's essentially taking it from here and stretching it 3 times. Stretching it 3 times. Or you can shrink it by multiplying the values here by 3. So instead of 1, you shrink it by 1/3. Of course, if you pick 0 everywhere, you're basically moving the vector to have length of 0. So you can shrink or stretch a vector by multiplying the identity matrix with some number, kind of like this. But you don't actually have to stretch every dimension equally. So, for example, if you want to stretch the first dimension by 2 and then stretch the second dimension by 3, you can do that as well. So, over here, notice how I had started with 1, 1. I stretched the first dimension by 2 and the second dimension by 3. All right, so you started from here and then you stretch them differently. So it's not just uniformly stretching them the same number. You have control over how much you want to stretch in every direction. Now that we know how we stretch and shrink vectors, what if we want to rotate vectors? Rotate vector. So in this particular example, the rotation vector in 2D, two dimension, it basically takes on the form like this. And the theta is simply the number of angles that you want to rotate clockwise. So if you want to rotate by, I don't know, 20 degrees, so you plug 20 into the sine and the cosine, and that's your rotation matrix. And it will rotate the vector by 20 degrees. Okay. Now, depending on the context, you might need to do it in degrees or radians. So, 2 pi is the full circle versus 360, the full circle. So, for example, let's say we have some vector 1, 1, right? So here's the vector 1, 1. Now we want to rotate by 40 degrees. So right now you can see that this is 45 degrees, right? 45 degrees. So if we want to rotate clockwise by 45 degrees, then it's going to end up here, right? So how do we do that? Well, we simply put 45 degrees, or you can put 5 pi over 4, depending on which mode you're in. And then once you put this matrix in, you have a rotation matrix. If you multiply the original vector by the rotation matrix, that gives you the resulting vector. So notice how after the rotation, the resulting vector is right here. Square root of 2 and 0. Okay, so this right here is an example of rotation. Now, that was rotation in 2D, but we have a standard rotation for 3D as well. So if you want to rotate around the x-axis or the y-axis or the z-axis, these are the very specific. These are the very specific rotation matrix that you guys we will use. This is the standard thing that we use. So we can basically rotate, like let's say we can continuously rotate a vector, right? So let's say every 0.1 second we rotate. So we take x and multiply by rotation by x. And then next 0.1 second, we'll take this and multiply again. And then we'll take this and multiply again. Every time you multiply by the rx, you essentially rotate the vector. So you can't. In mine, it doesn't show, but it shows on yours that this vector essentially rotates around the axis. Okay, I think. Let me see if I can show it really quickly. Right here. Yeah, here we go. So from here, you can see that it's rotating around the x-axis. And the way we achieve this illusion is essentially you take x, multiply by the rotation matrix, and then take the result of that and multiply by the rotation matrix again. All right, so let's go back. So that's the idea. The rotation matrix allows you to rotate around the x-axis. And now I think it's better if you can visually play around with this rotation idea. So I wrote some code to help you guys to help visualize. So in this specific code, you will need to import some of the libraries. But the idea is that first we create a vector at the location of 1, 1, 1. right? And then I add it into a task called rotate. So basically, every the code is going to generate new frames for the video, and every single frame it is going to call this function rotate. So what is happening every single frame? Well, we take the vector and then we calculate the rotation, and we're trying to rotate some kind of angle here. So we calculate the rotation, and notice how I start with the initial position of the vector, I multiply by the rotation, and that kind of moves the vector slightly. And then with the new vector, I draw. So if I just repeat this process every single time, I rotate it, rotate, it essentially gives the illusion that over time that the vector is rotating around the x-axis. Okay, so I have the source code here. You can download it and then check it out. Um, Alternatively, you want to take a second and try to understand it. So over here, I think, yeah. So this right here is saying that it's going to run at every 1/30 seconds. So that's how often this is going to run. So at this point, let's practice what we just learned. You want to download the code that I give you previously, that this example code. And then in the example code, it was rotating around the x-axis. But now I would like you to update the code so that it rotates around the z-axis and the y-axis. And you should look something like this. There we go. So you see how it's now on the left picture is rotating around the z-axis. However, the other one is rotating around the x-axis. Okay, so pause the video. Give it a try. See if you can change the rotation. All right, so now we're going to continue. So we went through one specialty matrix, which was the identity and the rotation. Let's go through more special matrix and vectors. So vectors and matrix, they can have other effects. So one of the vector that is really, really interesting is the vector of all ones. And we symbolically represent that as one. Okay, so what is that? Well, it's a vector of all ones. Sometimes we write vector of 4, which tells you that there are 4 ones in there. And if you transpose it, it becomes like this. But this is really, really interesting, and we use it quite a bit because it's a way of allowing us to add everything up. So, for example, if we have a vector v, and we want to add all the elements in that vector v, notice that this is v, right? Notice if we just multiply v by the vector of ones, it's equivalent to adding up all the numbers. So it's equivalent to a summation. And this is used like quite often to basically perform various tasks without using a for loop, right? You might need a for loop to add all these up, but instead you can just multiply matrix multiplication, and then it will just automatically sum things up. Now, but if the vector 1 can do sums, if we transpose the vector, it then makes copies of vectors. That's also really useful. So for example, we have a vector x here, right? Notice how if we multiply the x with an outer product with the vector of ones, it simply makes copies. It made 3 copies. And if you have more ones, it makes more copies. So you can make as many copies of the original vector you want. Now you might be wondering, why would we want to make copies of a vector, right? Well, making copies of vector could be quite useful. Like, for example, did I go over here? Yeah. For example, if you have a vector 3, 2. No, matrix. Let's say you have a matrix 3, 2, 1, 2, 0, 1. And what you want to do is for every single column, you want to subtract it by another one, another vector 1, 1. Right? Well, in this case, let's do 1, 2. You want in this case, the dimension doesn't match. And you want basically every column to do the same thing. Therefore, making copies in this case is really useful. Let's say we make 3 copies, right? So now it's 3, 2, 1, 2, 0, 1, minus 1, 2, 1, 2, 1, 2. So notice that every single column is now subtracting the same vector. Nice, and this is very useful when you need to do like this kind of operation later. Also, we sometimes combine two of them together. So over here, this you have the one vector right here, and then you have another one vector. Well, this has a very interesting impact because this creates together. It creates not it's not just a vector of ones. Now it's a matrix of ones. And now what it does is it simultaneously adds all the numbers together and make multiple copies. So you can combine operations together, right? So the first operation, you see, the very first operation you added together. But then after you're done with the first operation, you multiply by this again. And when you do that, then you end up making copies. So you're combining summation and copy making in a single matrix. Right? So this is saying that you can essentially perform multiple actions. Let's say we have the vector x. Well, we can multiply by the identity, and then we can multiply by the rotation x, and then we can multiply by rotation y, and then we can multiply by rotation z. And then what you can do is multiply all of them into a single matrix P. So P times X is equivalent to doing all these transformations. All right, let's put these ideas together. This enables us to understand this concept called the centering matrix. So the centering matrix, let's say we have a bunch of data, right? Like right here. We have a bunch of data. They're all stacked vertically. And then what we if we have this bunch of data and we plot them out on the plot, it may look like this. And a very common thing that we like to do is that we want to move this data to the center of the plot, which means we need to remove the average. So for every single point, we want to remove the average so that the entire cloud moves towards the center. And therefore, there's a matrix that does this called the centering matrix. So essentially, you have this data, right? X. All you do is multiply by the centering matrix, and now you will result in the data that move to the center right here. Now, I'm gonna show you later why moving the data to the center is useful. But for now, you need to know the definition of a centering matrix. So a centering matrix is defined as the identity matrix subtract by the one matrix divided by number of samples. So if you only have 2 dimension, then you'll be a 2 by 2 divided by 2 and then multiply by matrix of 1. Now, why does this work? Well, I wrote the proof for you if you're interested, but you don't really, for now, you don't really need to understand the proof. You just need to know that this matrix essentially is capable of moving a set of data into the center point. So, this is the center matrix C. X times C moves the thing. So here's the points, and notice how the points have now been moved to the center, whereas it was not centered previously. Now let's take a moment. Like, remember, the centering matrix is equal to identity minus 1 over n times the matrix of ones. So this is a matrix of ones. So the way you write identity is I, depending on number of dimensions. So that creates an identity matrix I. And then you can create a matrix of ones using this notation. And therefore, I minus 1 over n divided multiplied by 1 matrix. That's our centering matrix. So this right here is how we construct centering matrix. And then all we do is take the data and multiply by the centering matrix, and the result is now centered. So if we look at this plot here, right, that this is generated from the code we just looked at. We essentially have this data that's not near the center. After you perform centering, you multiply x by c. Notice how the data is in the center. And that centering matrix is quite useful, and we're going to use them like later in this lecture. Okay, so now let's look at this another example code. In this code, basically I generate a cloud points, a bunch of points in the cloud, and then I can move them. And the way I move them is I get the position, and then I shift the position, and I redraw with a new position. So you can see what is happening is essentially a cloud of points. That is, every time you press M, it will move the cloud slightly. Let me see if I can show you from the cloud. I believe is right here. So if you look at bottom right, notice how it's the cloud of points is kind of shifting. So that's what happens every time you push the M button. So that's what this code does. Right. However, here's the exercise that you guys are going to do. What I want you to do is when we press the M key, you're going to move the cloud to the center. So you can use this code as basis, but as well as the code we saw here. And your goal is to be able to move the cloud to the center. Okay? All right. So you want to pause the video and do this exercise. We're going to move on. All right. Next, how do we model movement? It's called interpolation. All right. Well, what I mean by that is if we have a point in space and we would like to move this point, all right, as if it's moving. All right. The way we can do that is basically we could, let's say we have a point at 1, 2, and then we have a point at 3, 1. So we're trying to move here to here. Well, I taught you that we could simply just add a vector, right? But sometimes we don't want to add the vector. What we want to do, we don't want to just jump to this point, because if you take the point, multiply by a matrix or add by some matrix, you would move this point. But let's say you want to create the illusion that this thing is kind of slowly moving this way. How do we do that? Well, we know that the initial point, x, let's say this is x here. If x adds some vector u, that's going to give our final location y. Therefore, we have the equation x plus u is equal to y. Right? You start with the vector, add some vector, and that gives us the final location. Well, this is interesting. That means if we know x plus u is equal to y, u must equal to y minus x. Okay, so this right here is the vector, the vector itself. So this means that if we know where we start and where we want to end up, this is the vector we need to add. Right? So what we do is we can count the time. We can do in the very beginning this u vector, right? We know the u vector. If we have x plus u, that's going to reach our destination. But what if we have x plus 0.1 u? Right? So this is 1/10 of the way to the y. And then, so every single time you do an update, you do x plus 0.2 u, x plus 0.3 u. So now it's 30% of the way to y. And every time you perform this update, You are basically redrawing the point and creating an illusion that it's moving. Okay. So here's another example. Here's a code. Basically, in this code, what what did I do? What did I do? Okay. Basically, I loaded a mesh. This a mesh is a 3D mesh is basically a 3D object. And then I position the 3D object as some starting point, and we're trying to reach some kind of endpoint. So whenever we press the M key, it's going to kind of initialize the whole thing. And what I did is I basically figure out that here's the starting point. Remember that was X. And then percentage, and this is the U, times the percentage of direction. So it, every single time we refresh the, the video, it goes and calculates it, and then it starts with u times 1%, u times 2%, so on and so forth. So that this creates the illusion that an object is moving. I think this code you need to take a quick look, and and it's better if you get to see it in action. So I think it's right here. Yes, right here. So you see how the point is kind of moving. You can like move the point. And the video I showed you looks like this. So basically I loaded a 3D object, which I call a Luffy, and then you can kind of like move this object through space. Okay, that's what it looks like. So okay, anyways, I want you to essentially download what I've done. This right here. I want you to download the code. I already give you the example code. So you can start with the example code. And now you want to move the starting point from here to here when the M key is pressed. So I want you to like try out coding this. Okay. And this is the result that it will move after you press the M key. All right, pause the video, do this exercise. I am going to move on. All right, what if you want to move multiple points? Okay, well, remember that if we want to move, let's say 2 points, well, we could take the first point, multiply by this matrix, and then take the second point. So we can do it twice. However, that is there's a faster way to do it. Instead of doing them individually twice, what we can do is we can concatenate them. So now it's 1002, right? 1002. So instead of multiplying them individually, what we could do is make them into a bunch of columns, and then we multiply. And notice then you get the first result as well as the second result. And this is much easier than if you try to do them one at a time. So this is, and the idea continues. Let's say you have many points, and you're trying to rotate them, all the points simultaneously around the x-axis. You simply concatenate them, all the vectors, into a single matrix um, as columns, and then you just multiply. And the resulting points would be the points rotated by some kind of angle. So that was rotation, right? You can also move multiple objects. So I think I showed you previously. If we have a bunch of vectors, vector 1, vector 2, vector 3, well, and you want to move them by 2, 2. All you have to do is make copies of 2, 2 multiple times. So you take the all your vectors and then you add 2, and depending on how many copies you want, you will be able to simultaneously move all the points. Okay? All right, so over here, here's another example. Let's say we have a stick figure, like an object, connected by dots, and the points are here. And of course, if we want to like move it somewhere, what we would do is we will essentially take all the points, so every single column is a single point, and then add it to some kind of vector that you want to move. And then you multiply by 1. Right? So this will essentially move it to another location, all the points simultaneously. And the way you write is this: you take the data, and then some vector you want to move, and you make multiple copies of them. Right? So right here you see, I want to move by -3 and 1. And then I made multiple copies of them. Then I add them together, resulting in simultaneously moving every single point. So that's how you go about um, moving like all the points. This is how you go about rotating all the points simultaneously. Now, you would, if you end up working for, I don't know, Disney or something, you would need to notice how a lot of 3D models are basically just points. You would need to deal with millions of points. And therefore, you would need to like rotate or do some kind of action simultaneously. And the way we do that is through matrix operations. Okay, so now we learn how to rotate. I think we learn how to move. Now we need to learn how to scale the object. Okay, if we want to scale the object, well, like let's say we want to turn this into twice as big, right? Twice as big. The key here is you actually need to move it to the center, then you scale it. Then you will uniformly scale in all the sizes. So the way you do that is you take all the points and multiply by the centering matrix. So that will move it here to here, like such. And then let's say you want to multiply by 2. You want to twice as big. Then you simply multiply 2 by this. Or you can do move it to the center times 2. So you will essentially move it to the center and expand the size by 2. Of course, instead of 2, it's 1/2. It means you're shrinking it. So you can kind of make an object bigger or make the object smaller accordingly. Okay, I wrote that right here. Okay, so now let's see if we can practice. Let's do a quick practice of transformation. This is the stick figure, and let's say that you work at Pixar, and your boss is um is telling you that whenever this character gets mad, it becomes bigger, standing in the same place but bigger. And your boss essentially wants you to write the transformation. How do you go from the original data, multiply by something that will create this transformation? Okay, essentially doubling the size of your Disney character. Okay, and then see if you can draw out the final to make sure you got it correctly. So that's your next exercise. Okay. I provided the solution here as well as here. The key is you want to basically center and then double and then move it back. Okay. All right. The final project of today. Basically, your goal is to generate a special effect of explosion or galaxy explosion away from the center, and let's see if we could see what it looks like. I think it's right here. Right here. Yeah, you can see from the picture, right, that essentially you can picture a galaxy contracting, and then at some point it gets small and then it kind of explodes again. And you want to simulate this effects. So you want to rotate and you want to move it to the center and rotate and move it back, right? And then you need to do that in real time. And as a result, you will have this kind of effect. Now, if you were not to, if you forgot to center it, then your rotation will look like this, which is not what the effect we want. Okay, so this is, I think this is all for today. I will see you in the next class. Okay, bye.